So I think we can get started. This week we have Nathan Leigh, who's here from the American Museum of Natural History. He was actually an undergrad here, then went to do his PhD at McMaster, and then was a fellow at the European Space Agency in the Netherlands before coming to the American Museum of Natural History. So he's an expert in gravitational dynamics of stars, and he's going to tell us about some of his work on modeling the chaotic dynamics in globular clusters.
Star cluster environments, yeah.
General star cluster environments. Okay.
Thanks, Dan. Thanks for having me. It's wonderful to be here again. I also owe thanks to the Center for Computational Astrophysics and David Spergel, as well as Rosalba Perna and Stony Brook University for my funding. But I am at the American Museum of Natural History. And the work I'll be talking about today was done in collaboration with Nick Stone, Aaron Geller, Mike Shara, Jeremy Webb, who's in the audience, student Tim Ibragimov, and Johan Samsing. All right, so let's start simple. So two bodies make a binary. No surprises here. Thanks to pioneering efforts from Newton and Kepler, this is a solved problem. So we know the positions and velocities of two gravitationally bound objects at some initial time, and we can predict their positions and velocities at a future time. The orbits are periodic, and no chaos is present. So if I could take a giant finger and perturb the system on the left, I would get back out some long-lived steady state like this more eccentric system on the right. But if we add in a third body, all hell breaks loose. So the general three-body problem is a well-studied example of chaos in nature. And I am showing a numerical scattering simulation of a single binary interaction, courtesy of Aaron Geller. And these types of interactions occur very commonly in dense star cluster environments, such as globular clusters in the halo of the Milky Way, or even the galactic center. And oftentimes, one or more of the participants is actually a stellar mass black hole. And so these interactions can proceed for millions of years until eventually they disrupt via the ejection of a single star, leaving behind a binary. But the overall evolution is in the form of you're generally left with a temporary single star and a temporary binary star system, with the single star continuing going off on long excursions. And the idea here being that for the general three-body problem, if you're given the positions and velocities of all three particles at some initial time, there is no simple analytic solution to predict their positions and velocities at any future time. Okay, so what formally defines chaos? So I have here an example from Hanamaki et al. That is looking at a series of numerical scattering experiments of single binary interactions. So encounters very similar to what I just showed. However, in this case, they release all three particles from rest. And so on the x-axis, we have a measure of time in units of the crossing time. And on the y-axis, we have a measure of distance from the origin. So this is actually the distance separating the particles in a homology map, but it's much more straightforward to simply think of these as the distance of each particle from the system center of mass, and the behavior, the characteristic behavior is basically the same. So what these authors do, they perform many, many numerical scattering experiments for a fixed set of particle masses, initial energy, and angular momentum. And each time they perturb the initial conditions very slightly. And what we find is that initially, for the first few crossing times, the particles follow their previous trajectories quite well. But if you integrate for very long periods of time, then these small perturbations induced at the beginning can compound, and you can get out a completely different outcome than you did in a previous numerical scattering experiment. And so we can characterize these outcomes. For example, one particle is always ejected. Which of the three particles is that, and what is the probability for this to happen? And so the basic idea is that for a given set of initial conditions, so particle masses, energy, and angular momenta, for a chaotic system, we get out a distribution of outcomes. And so this is effectively what formally defines the chaotic systems we'll be talking about today. So you can use like a Lyapunov exponent if you want to actually figure out timescales on which these trajectories start to diverge for a given perturbation. So another example of chaos. So this is a topological map showing n states of binary single scattering, courtesy of Johann Samsing and a student he's working with at Princeton. And the basic idea here, so these authors ran millions of numerical scattering experiments between a single star and a binary, where all three particles are black holes with masses of 10 solar masses. What the authors do, so for each experiment, they take the binary and they reorient it very slightly, and then they reperform the experiment. And so reorientation of the binary is quantified down here on the x-axis via the binary phase. They also perturb the incoming single star initially, so changing its velocity and the angle at which it's headed towards the binary very slightly. And so the measure of that is the impact parameter on the y-axis. And every time they run a simulation, the authors, they get out an outcome. And so they're able to classify the outcomes here using a color scheme to color code each of these different outcomes. So yellow, blue, and orange correspond to the three different possible exchange scenarios. So you can kick out one of three of your initial black holes. You can also have direct collisions shown in black. So the authors consider finite sizes for their particles and include gravitational wave emission. And you can also get gravitational wave inspirals, which are shown in red. And so every time the authors perform a numerical scattering experiment, they get one of these 6 outcomes, and they put a point on the plot with the appropriate color for the outcome they get. And so Johann actually showed these in an art gallery at Princeton University, since they make for quite pretty images. And so we see some characteristic behavior here. We see swaths of uniform color that correspond to regular behavior. So if you perturb your initial conditions only slightly, you get back out the same outcome that you would get if you were in an adjacent region of parameter space. But we also see regions of what appear to be true chaos. So regions where slight perturbations to the initial conditions give you a completely different result. And we can zoom in on these regions to resolve them in a little more detail. And what we find, actually, you see some micro topological structures that are appearing in phase space. So if we're heading along one of these paths here, we will stick to this blue exchange scenario, and small perturbations to the initial state don't affect the outcome. But these types of regions of regular behavior are always neighbored by poorly defined crossovers into chaotic portions of phase space. And so given the author's choice of step size for perturbing the binary and your single star, they still see regions of true chaos in their simulations. Okay, so the takeaway from this is that for a given set of initial conditions, for a truly chaotic system, there is a distribution of outcomes. And so you might ask, so why is this an issue in astrophysics? The basic point being that in astrophysics, we often have to run one very computationally expensive simulation, so particle numbers of the order of millions or more. And these simulations, the computational expense scales as number of particles squared, so they can be very computationally expensive. They can take months to run a single simulation to completion. And if you know that if by perturbing your initial state, you're going to get out a completely different outcome, then this begs the question, how can you trust the results of a single simulation? And so an example of where this might be important, if you're running n-body simulations of star cluster evolution and you want to know the time scale on which your star cluster dissolves to feed its stars into the field of the galaxy, this should actually be some sort of distribution of disruption times. And so in order to populate that distribution function, ideally you want to run lots of simulations, each time perturbing your initial conditions very slightly. And to do this with current n-body simulations of star cluster evolution is computationally prohibitive, and it's not something we can really do yet. And so to help drive this point home a little further, I have an example courtesy of Dan Tamayo and Hannah Rain, looking at the Janus integrator they recently made. And so Dan, please step in and correct me if I say anything incorrect about the integrator. But this is actually a really nice example, I think, of exactly the concerns that I've been talking about. So what these authors have done is, so they've set up a bitwise integrator that is strictly time reversible. And so they set up initial conditions where they spell out the name of the integrator Janus, and they use 1,000 particles. They release the particles from rest at time t equals 0. Gravity is the only source of acceleration. And then they iterate forward for 500 time steps. And they get out this intermediate state after 500 time steps. And because the equations of motion are time symmetric, then upon flipping the sign of the velocity and integrating forward for another 500 time steps, a truly time reversible integrator will give you back exactly what you started with. And so with the Janus integrator, which is bitwise and was designed specifically for this capability, this is the reality, and you do recover the initial conditions that you started with. However, the reality for most star cluster simulations is that they're using a leapfrog integrator, which is not strictly time reversible. And so another example of this same sort of experiment has been set up for a typical leapfrog integrator. Spell out the name of leapfrog with 1,000 particles, release them from rest at t equals 0, get your intermediate configuration, and then flip the sign of the velocity and integrate forward for another 500 time steps. And the authors in this case do not recover the initial conditions that they started with. And so the key point here is that computational error can actually get you and make it so that your simulations are not truly time reversible. And so again, this begs the question, how do you trust a single simulation? And really, you want to be able to run many n-body simulations for any given initial set of conditions. Also, if there are any questions, please just feel free to jump in. Ask me as I go. Right, OK, so what does this have to do with black hole? Sorry?
The scheme is reversible when you write it down on paper.
Right.
But so unless you program it in a special way, it's not going to be in your simulation. Just because of the roundup.
Just of the roundup.
Yeah. So if you have a very chaotic system, eventually you will get completely different.
The Janus can go around the roundup.
Well, we probably seem to suggest that the coded property could be reversible. But you don't. That's just the way you
Not the
use it.
roundup.
Yeah, and so the way you guys deal with that in Janus, I think, if you can, again, you kind of just grid up your phase or your position space, and you can kind of decompose, get rid of your round-off integrator or your round-off errors by turning everything into some sort of integer count for your positions in x and y space. And then the way a particle will move through this space can only occupy specific cells within it. And so it's so then it's straightforward about how you time reverse this scenario. Is that the basic?
It's hard to do the forces and floating point.
Right.
But, yeah, I think.
Okay, analogy. Sure. Okay, so star cluster simulations, and what does this have to do with black holes and gravitational waves? So to just give a brief overview of something I'm sure most people are familiar with here. But LIGO came on the scene recently and has been detecting the mergers of black holes. So I think we're up to a count of order 3.5 at this point. And so this is a figure showing the four-ish systems that LIGO has currently detected. And on the y-axis, we have solar mass or the masses of both the progenitor black holes that merge to form the more massive one. The takeaway from this is that what we're actually seeing is that we're seeing more massive black holes than we've ever really been able to see before at the stellar mass scale. So there's a comparison here to previous X-ray studies that were able to actually constrain the mass of the black hole via getting orbital parameter information. And the masses of these black holes are typically much, much lower than what LIGO has been detecting. And so there are some biases here, obviously. So for example, in order to be able to detect a black hole in a binary star system, you need it to have a luminous companion, at least before LIGO turned on. And so these black holes all had to have a stellar companion, and so that pushes the mass of the companion down relative to the masses of some of these black holes. So there's one bias. Something else that people have noticed, people are intent on trying to understand the spins and how the spin axes of the progenitor black holes add up to form a spin in your final black hole, with the idea being that whether or not, if the spin axes are aligned or not aligned, this is something of a useful probe, potentially, of the astrophysical environment in which these mergers are occurring. So for example, if you have two black holes that are formed from two massive stars in an isolated binary star system in the field, there are arguments you could make where the spin axes of both black holes would stay aligned with the orbital plane of the binary. And so for this scenario, you would actually expect the spin axes of the two progenitors to be aligned upon merger. Whereas if you form these black holes in a very dense star cluster environment, there's no real reason to expect that the spin should be aligned. And so I'll talk a little bit about the astrophysical environments where these types of mergers might actually be happening. And so just to show a quick simulation of one of the in-spiral events detected by LIGO. So we see both of these black holes gravitationally bound in a binary star system. And that is the takeaway of this slide, really. In order to get two black holes to merge for detection by LIGO, you need to somehow get them bound in a binary star system first. And how to do this is currently an open question. So eventually what we'd like to do, as LIGO keeps detecting these mergers, we'll hopefully get something resembling a mass function for these black holes. And using that mass function and potentially a spin distribution, hopefully we can say something about where these black holes first originated. What astrophysical environments did they come from? Did they start out in binary star systems? Were they swapped into binary star systems in a very dense environment, et cetera? And so in this simulation, you see the gravitational waves propagate outward for eventual detection by LIGO. Okay, so let's get into this question. What astrophysical environments birth black hole binary mergers? Currently an open question, but we know that all stars arguably are born in star clusters, and by extension, we think that all black holes should also originate in clusters. And so what do we think these clusters actually look like? So a popular choice are globular clusters that exist, for example, in the halo of the Milky Way. So these behemoths have masses on order of 1 million solar masses. So they're very, very old. They tend to have ages of 10 to 12 billion years, so their ages are comparable to the age of the galaxy or even the universe itself. The mass of the main sequence turnoff in these things tends to be of order 0.8 solar masses. So all stars have masses less than about 0.8 or so. The central densities in these clusters can get to be about 10 to the 6 or higher solar masses per cubic parsec. And so to put that into perspective, in the solar neighborhood, our next nearest neighbor, Proxima Centauri, is a parsec away. And so if we took that pair and we put it in the core of a globular cluster, we'd find that within roughly a parsec volume, we'd have about 1 million stars, whereas in the solar neighborhood, there's only one. So much, much denser environments than in the solar neighborhood. And the densities are so high, actually, that encounters between single objects and binary star systems, as well as between two binaries, are thought to occur quite commonly. So the timescale for these interactions tends to be of order 1 million years, 1 to about 10 million years or so in a typical globular cluster, with a fraction of unresolved point sources that are actually binary star systems. That's of order a few percent. You'll find that single binary interactions are dominating and that your binary-binary interactions are happening at a pretty comparable frequency. And oftentimes, as I mentioned, one or more of the objects involved in these interactions are compact objects like stellar mass black holes. And so I have a simulation showing the time evolution of a globular cluster type system, courtesy of Anna Sippel and Jeremy Webb. And Jeremy will have to correct me if I'm wrong, but I believe the red objects that start appearing in the center are black holes. And the basic idea is that stars kind of orbit about the cluster potential on rosette-shaped orbits. So 1 second in our time corresponds to about 1 million years in the simulation time. And these black holes all tend to be more massive than other stars in the system. And so because of energy equipartition, they tend to sink in towards the cluster core and occupy regions very, very close to the center of the cluster. And so the idea being that all stars want to have approximately the same kinetic energy. So if you're a more massive object, you're going to get a reduction in your velocity. You'll slow down and sink deeper into the cluster potential. So most black holes in these massive globular clusters are right in the core where the stellar densities are at their highest. And so this is the picture everyone should keep in mind when thinking about dynamical interactions in the cores of globular clusters. And so we can actually ask, so let's say we zoom in on a particular black hole in the core of a particular globular cluster, and we'll follow it as it makes its way through the core. So in a relatively short time scale, the black hole will encounter a stellar binary, and we'll have a temporarily bound chaotic three-body interaction that proceeds more or less as we saw before. One of the key points of these interactions is you always end with the ejection of a single star, assuming you have point particles and collisions are not possible, or you're not actually trying to model collisions. And it is almost always the least massive star that is ejected from the system. So systematically over time, if black holes are undergoing these single binary interactions, they will tend to be exchanged into stellar binaries, kicking out one of the stars in the process. And so in this particular case, the incoming black hole will get swapped into the stellar binary, kick out the lower mass star, which will eventually happen. And in this case, they follow the star that gets kicked out, and it encounters another binary star system. This interaction will end in a direct collision between two of the objects. However, we could have just as easily followed the other binary, which now has a black hole swapped into it, and that binary may very well go off and encounter another stellar mass black hole, and the process repeats. And since it's the most massive objects that tend to be left gravitationally bound in the binary, you've systematically turned a stellar binary into a binary composed of two black holes. And this is what we need in order to have these two black holes later merge for detection by a LIGO. So many people have argued that globular clusters are potentially efficient factories for the formation of black hole binaries. And if this is correct, there is potentially a lot of astrophysics information we can extract from the observations that a LIGO is taking. So we stand to learn about the formation of globular clusters, how their stars formed, evolved, and died to make black holes, as well as a number of other issues. Unfortunately, there's a lot of uncertainties here, and so I'm going to talk about, in particular, how we can tackle the cluster dynamics in going about understanding how you take some set of initial conditions in a primordial star cluster and fast forward it through time to get out black hole binaries that eventually merge for detection by a LIGO. So to just paint a general picture, let's say that we know how stars form in globular clusters. So we know the masses they had, what fraction of their gas got turned into stars, the stellar initial mass function when this happened, the maximum mass of the most massive star in the cluster. Let's also assume, so we know the properties of all the stars. Let's assume that we also know how these stars then evolve and die to form black holes. We know this actually quite poorly, so massive star evolution is currently quite uncertain. We can also assume that initially we know how many black holes start off in binary star systems. Let's also assume that we understand and can correctly model all of the internal evolution that happens in binary star systems. If we can do all this, which we by no means can at present, then this still only brings us up to about a few hundred million years after the birth of the cluster. But globular clusters are billions of years old. So this leaves us still with of order 10 billion years of internal dynamical evolution that we need to worry about. And so I'll talk about how we can actually handle this internal dynamical evolution analytically. And so the basic idea here is that when trying to cover the parameter space and run simulations of star cluster evolution for a given set of initial conditions to produce something that we can then try to compare to the observations being taken by a LIGO, there are really two major challenges to overcome. So first of all, these are chaotic systems. So for one set of initial conditions, one simulation is not really enough to adequately sample the distribution of outcomes that you would expect. And there's also an initial conditions problem. So really, the initial conditions are very poorly constrained. We really don't know what globular clusters looked like when they were first forming. And so what one might want to do for this type of problem, or the naive approach, would just be to say, well, I'm just going to throw computer simulations at it. I'll start running as many star cluster simulations as I can. Each time I'll choose a set of initial conditions, I'll perturb them slightly, I'll run the simulations, I'll get out a distribution of outcomes for that initial set of initial conditions, and then I'll change my set of initial conditions and do the experiment again. And then I'll look at what I get out, and I'll pick the subset of simulations I get that matches up best with a LIGO, and then this will tell me what initial conditions evolve through over a Hubble time to give me what a LIGO is actually observing. If you want to do this way, realistically, this will take thousands, millions, maybe even billions of computer simulations to do. So it is completely unfeasible at this point, given modern computational limitations. And so what I'll talk about is taking an analytic approach to modeling the chaos in single binary and binary-binary interactions such that we're able to reduce the problem to just an initial conditions problem. So the idea being we choose a set of initial conditions, and then we can correctly account for the chaos in order to avoid having to run many simulations for every set of initial conditions. And so I'll talk about an approach that I've been developing with Nick Stone to do this. So what we're basically going to try to do is we're looking at some initial population of stellar mass black holes in a given globular cluster with a given set of initial conditions. We want to correctly handle the internal cluster dynamics, so how these things undergo single binary and binary-binary interactions, to give us these black hole binary pairs that a LIGO is currently observing as merger events. And so Nick and I take a statistical mechanics approach to the problem. So in the 70s, J.J. Monahan, who was one of the original people who came up with the idea for smooth particle hydrodynamics. He also spent some time working on the chaotic three-body problem. And J.J. Monahan used the density of configuration states per unit energy to calculate for the chaotic three-body problem what you would expect for a given set of initial conditions. So you choose your particle masses for all three particles. You choose an encounter energy. You choose an angular momentum. And then you map this to a distribution of outcomes. So you can get things like the distribution of binary orbital energies for the leftover binary in these three-body interactions. You can also get the ejection velocities for the single star. And you can get probabilities for which particle will actually be the one to be ejected. And so Nick and I have been taking this formulation and adapting it to the chaotic four-body problem, with the general idea being that for all point particles, the three characteristic outcomes of chaotic four-body interactions with negative total energies can all be described as some variation of three-body scattering. And so an example would be if you eject two single stars sequentially, leaving behind a binary, this is two back-to-back three-body scattering events. And so we try to adapt the three-body formulation in this way to treat the four-body problem. So just briefly, if you're running a scattering simulation between two binaries, so I showed scattering simulations between single stars and binaries. Imagine we replace one of the single stars with another binary, and we launch these binaries directly at each other. So we do this, we choose a well-defined initial state, and really just vary the relative inclinations between the binary orbital planes. But we keep the relative velocity at infinity fixed and the properties of the binaries. And we perform many simulations, millions of simulations for that given set of initial conditions. And if you have point particles and negative total energies, there are three possible outcomes. So you can get back what you put in. You put in two binaries. You can get back out two binaries. You can form a stable triple and eject only one single star. And so this stable triple is characterized by a large ratio between the inner and outer orbital separations. So the outer hierarchical triple effectively sees the compact inner binary as a single object, since this ratio is very, very large. And if this is true, then we call the triple hierarchical, and it can be stable for many dynamical times. And then the last case is if we sequentially eject two single stars, leaving behind a binary star system.
What's understood about how the distribution of star triples of ordinary stars has been modified by Gauss?
Very, very poor, I would say. I think we have observations of stable triple systems, but we don't know how they formed.
About how the instance of triples evolves with stellar age or dynamical age?
No, so I think, well, one of the major problems here, we're pretty restricted in the way that we find triples right now. You have to, in general, it's much easier to find them in the field. We have found them in open clusters, but in globular clusters, there's very little hope of doing this, since you'd have to do it photometrically. It's actually something that we're trying to do right now, since Hubble Space Telescope has now done 2 epochs of surveying the entire Milky Way globular cluster population, the baseline of about 8 years. So you can now do proper motion cleaning, and there is actually the potential to identify objects photometrically that can only be triple stars. But we have a very poor handle on what kind of triples are out there, really. It's much harder than a factor of 2 to find a triple than a binary. For example, like a radial velocity survey, you have 2 chances that you'll have an orbit face on instead of just 1. Okay, so for each one of these encounter outcomes, we get distributions of binary orbital energies for leftover binary, leftover triple, ejection velocities for all single stars and multiples. We can also do the relative or the distribution of inclinations between the inner and outer orbital planes of dynamically formed triples. So the potential to actually predict for a population of dynamically formed triples what subset of them will actually be in the active lit-off Causality domain. Just to show you a comparison of what we have so far between our analytic work and the results of numerical scattering simulations. So the dotted lines are showing our analytic predictions, and the solid lines are showing the results of our numerical scattering simulations. So blue is the 2 + 1 + 1 outcome. Black is formation of a stable triple and a single, and red is 2 binaries. On the left plot, on the x-axis, we have binary orbital energy of the most compact binary left over. So in the 2 + 1 case, it's just the 1 binary. In the triple case, this is the inner orbit of the triple. And in the 2 + 2 case, this is the more compact of the 2 binaries that are formed. On the y-axis, we have effectively number of simulations or a normalized fraction. So if we integrate the area under each curve, it'll be unity. And what we're finding is that we're able to predict the power law dependencies for these distributions of orbital energies quite well. We also look at ejection velocities for the single stars formed in both the formation of a stable triple as well as the 2 single stars ejected in the 2 + 1 + 1 case. And again, if we overlap our analytic predictions with the numerical simulations, we find quite good agreement. And so it's just to briefly say, so the assumptions that go into this, we assume ergodicity, so the available phase space is populated uniformly. And this assumption actually turns out to be quite good for most interactions in globular clusters involving black holes. So the assumption of ergodicity is upheld generally quite well at low relative velocities at infinity. You can really just think of the assumption as ergodicity as corresponding to a long-lived resonant state where all 4 particles are effectively mixing in phase space. And so at low virial ratios, it holds, and provided your particle mass ratios are not too extreme. And so it happens that for black hole subpopulations in globular clusters, if you actually calculate the distribution of virial ratios you'd expect, that they generally pretty much 97 to 98% of all single binary or binary-binary interactions satisfy the requirement on the relative velocity at infinity in order for your ergodic assumption to be valid. So for the black hole populations, it turns out that our analytic formalism should be quite applicable and be able to cover most of the parameter space once we figure out this excess here at larger orbital energy. But I think that we're starting to actually understand this. So this is corresponding to the very widest binaries and in the three bodies. So this is actually something that people can't fit in the standard three-body problem. I think it's one of the last things people have to work on. And so we've recently realized that part of the reason that our analytic formulation is breaking down is related to causality criteria. So if you think about in the three-body problem, you need to eject a single star, but also leave behind a very, very wide binary. At some point, you're going to be causally inconsistent. So in order to eject a single star in a three-body configuration, you need all three stars to be in a relatively small volume. As you're making your binary wider and wider, this is becoming harder and harder to satisfy. And so this is actually why, theoretically, all of these distribution functions diverge at very low binding energy. But in the simulations, we see a turnover at this critical orbital energy.
Are these analytical expressions, like the dotted lines?
Yeah, the dotted lines are all analytic.
Those expressions that can easily use for phase-space integrals?
Yeah. So I mean, so the way that we do this is we write down the density of configuration states per unit energy, and so you have like an integral. So if you use sigma for your density of states, you have a bunch of integrals over your available phase space, right? So this is completely unconstrained. But if I put a delta function in the integrand with an energy dependence that is only non-zero when energy is conserved, then this integral is only non-zero when the requirement for energy conservation is satisfied. So you can rework the delta function and then perform as many integrations as possible to get like an expression with dEB for the orbital energy distributions and then dE for the eccentricities.
So yeah, my question was if you guys can actually solve that.
Yeah. Yeah, so it's all the dotted lines are analytic, yeah. And the dashed are simulations.
What do you mean by ergodic in this particular interval?
So you're assuming, so for example, if you throw two binaries at each other and you just split apart one of the binaries immediately and then the two stars go off and escape as single objects, your assumption of ergodicity is not satisfied. You need all four particles to undergo a long-lived resonant state and mix effectively.
Which means when you're doing your analytic calculation, what simplifies?
What simplifies?
What is assuming ergodicity by you?
Assuming ergodicity, what does it buy you?
You're actually doing an integral with a smooth R and P, I guess is what you're saying.
Yeah, so that you break apart the integral. I mean, if you have, in the three-body problem, you have,
The only constraint is that E has to be E0.
yes.
That's the assumption.
That's not. So you're mentioning about chaos and ergodicity, so I was wondering how you, I mean, if it's a non-chaotic system, surely you're going to get very different results.
Right, so we only get the right results when this assumption of ergodicity is upheld.
So what this assumption of ergodicity comes out to mathematically that seizure?
So you're assuming that your phase space is populated uniformly. So basically, the volume in phase space.
Measure there. That measure d cubed R, d cubed P. That's not true in general for a Hamiltonian system. With just a simple delta function.
Well, surely that's not,
No,
That's
it's not
not
correct.
uniform.
It's an assumption that he makes, so you can do the analytic inverse. And it seems to work reasonably well. That's
assuming the phase space density is uniform.
the orbits cover things uniformly. That's why you're going down and measuring your orbit down.
How does that compare energy? I mean, the fact that there's a.
Well, no, he puts a delta function in it puts an energy, but that's the only integral. He's assuming that that's the only integral of motion. That's what he means when he says it's ergodic.
This is, okay, all right, I was too, I mean, there's only particular hyperdimensional space which satisfy that total energy term. So
Yeah,
it's
that's
not
right.
really ergodic whatsoever.
No, it is ergodic. Ergodic means you're,
Within that energy surface, yes, but otherwise
it's a Hamiltonian system. So ergodic means you're conserving energy, so you're restrained to an energy surface. That's
Yeah.
what that means. And what's funny about it is that there are other integrals of motion in the system, and they don't appear to make any difference. Because he's assumed they're not there.
You mean
He
that
gets
has
an answer
momentum?
which is right. Yeah, no momentum or anything else, exactly.
So yeah, so in the original formulation, Monahan makes assumptions about angular momentum. He assumes either low angular momentum or high angular momentum to make the integrals easier, but there should be an angular momentum delta function in there as well. That should also only be non-zero when angular momentum is conserved. And so this is something Nick and I have been working on, is redoing the original three-body formulation, putting in a delta function for the angular momentum integral, and then reworking it from scratch. And before, they've always had to assume they know the angular momentum going in, and they've done a parameterization from numerical scattering experiments to handle variations in angular momentum, how changing the angular momentum affects the shape of these distribution functions.
But you didn't do that for this calculation.
No. For the four-body problem, yeah, no, we haven't done that.
So you just assume it's not conserved. And it works. Except for the...
fine.
Except for,
Still
yeah.
amazing magic.
Magic?
One of the challenges of these sort of mechanics treatments was that especially when you have multiple bodies, and you can put one of the bodies at infinity, the volume, the phase space available to infinity is infinite. You get it all the way out there, and then you get to the position. So how do you regulate? Usually you end up with divergences. How do you regularize that kind of divergence in the phase space available to the effective body?
Yeah, so one way is causality criteria. So for example, there are certain ejection scenarios that are just not causally feasible. So like I was saying, like if you want a three-body ejection, everything has to be in a relatively small volume, which kind of prohibits you from making the widest binary you could possibly want.
A small cutoff in the size of the remnant binary, which cuts off some volume of phase spaces that we get.
Exactly, yeah. So yeah, I kind of think of it as you need to get some sort of strong deflection happen, and you can't have that happen in certain regions, certain coordinates of parameter space, and so that's why you see those regions not actually being filled.
Well, maybe because it compensates, right? You need a very high boundary.
That's the point, is you can get very tight binaries. So if you assume ergodicity, which allows you to trade the evolution by saying you have equal probability just to be in every available cell of the phase space,
Right.
then you end up with these divergences. So it sounds like you're putting in a small scale cutoff, which like the binary can't be too tight, and then conversely you cut off the volume.
But the probability getting those very tight boundaries is also very, very small, diminishingly small, so compensation is large.
Maybe. So that's what I'm asking.
Yeah, so maybe we can come back. I'm not sure if I... Sure. Okay, so what can you potentially do with this? So, I mean, ideally, long-term, what we'd like to do is sort of take the Monte Carlo framework for globular cluster evolution, where you're using sort of a global field-based approach to handle the cluster evolution, and then you're calling on a few-body scattering code to do like the single binary and binary scattering experiments. And there's the potential here to replace the scattering code with something of a more analytic formalism and actually propagate distributions forward through time in order to get out, for a given set of initial conditions, the appropriate set of distribution functions for your black hole binaries that you think are going to merge relatively soon for detection by a LIGO. And so kind of just an example application sort of heading in this direction. We looked at three-body scattering in galactic nuclei and how dynamical hardening of black hole binaries in galactic nuclei contributes to winding down the orbital separations of black hole binaries. And so just to kind of give a brief explanation of this plot. So what we do is we take 10,000 black hole binaries. We're thinking about the galactic center, so the nuclear cluster at the center of the Milky Way. So this has a velocity dispersion of order 100 kilometers per second, a central density reaching, I think, 10 to the 7 solar masses per cubic parsec at its highest. And so we put each of these binaries, we put at the influence radius, which gives us a rate of encounters with single stars in the surrounding nuclear environment. And then for each black hole binary, we randomly sample some initial separation between about 1 and 10 AU. And then we ask, so if we run for each black hole binary, we have a time scale for the black hole binary to be encountering other single objects and experiencing these three-body scattering interactions. Then we can simply perform or calculate analytically what the outcome of each of these three-body scattering interactions is. And then in between each scattering interaction, we could just use the Peters formula to calculate the effects of gravitational wave emission on reducing the orbital separation and eccentricity of the black hole binaries. And so we take 10,000 of these with various initial orbital separations. The masses of the components are 10 solar masses and 15 solar masses. All interloping single stars have a mass of 1 solar mass. And then we ask how many direct single binary interactions does it take in order to wind each black hole binary down from its initial orbital separation to an orbital separation that is sufficiently close that the black hole binary will in-spiral and merge due to gravitational wave emission before the next encounter happens. And so using the analytic formalism for various assumptions about how you think the scattering will happen, so the total angular momentum of your scattering scenarios. So you can assume purely isotropic scattering, which is shown in the red, or you can assume purely planar scattering, which is shown in the blue. So planar would be something like you might see in a disk scenario. Isotropic is just a spherical cluster. And so the solid lines show an analytic calculation for how many direct single binary interactions you actually expect to have happen in order to wind the black hole binary down to that critical point of rapid in-spiral. And so we calculate the expected number for both the isotropic case as well as for the planar case. And what we find is that the planar case is actually much more efficient at winding down black hole binaries and getting them to merge. So we're seeing some effects. So there's two reasons for this. So basically, the first reason being that the ejection velocities for the planar scattering, it's a much broader velocity distribution. So the probability that you'll fire out a single star at very high velocity is higher than in the isotropic case. So what this means is that for a given black hole binary, in the planar case, the first encounter is going to effectively harden the binary, or more effectively harden the binary relative to the isotropic case. So when the second interaction happens, there's a non-negligible probability in the isotropic case that the total energy of the encounter will be greater than 0, and you'll actually disrupt the black hole binary. And so in a galactic nucleus with the velocity dispersion of 100 kilometers per second, most of our binaries in our simulations are actually disrupted long before merging. And so that's why we actually see the red being pushed down to the blue, because in this case, in the isotropic scattering, it's only those initial three-body interactions where you're sampling a high relative velocity or a high final velocity for the single star that actually end up surviving to the point of merger, and the rest are actually disrupted. And so in the planar case, it's more effective. This is generally more effective, and it's a lot easier to quickly wind these things down to very compact orbits.
So what do you mean by disrupted?
So disrupted is just if the total encounter energy is greater than 0. So basically, you're sending a single star in, and then you're asking if it's going to rip apart the black hole binary, unbind the binary pair. And so in galactic nuclei in general, that process should be very efficient. So the velocity dispersions are really, really high. And so if you're just sampling from reasonable distribution functions, most of your interactions will have a positive total energy, and you'd expect most interactions to actually disrupt the black hole binary. Right. But in sort of the more rotation that you have in your nuclear cluster, effectively, the more you'll be pushed towards more planar scattering on average. And so this is basically pointing to a scenario where if you want dynamical hardening to play an important role in getting black hole binaries to merge, it's going to be easier in clusters with significant rotation or anisotropy. And so the extreme case, which is something I've been looking at with some collaborators lately, is if you're in a deeply Keplerian potential with an AGN disk or something, and you can think of some scenario where everything has been ground down into the disk, and so all of your interactions are going to be planar and have low relative velocities because they're all incoming in the same plane on Keplerian orbits. So for example, if you're thinking about a migration trap in an AGN disk and you get a black hole binary stuck there, this might be a good place to have interactions, kind of if you have type 1 migration, bringing stars or other black holes in, then the scattering will be planar, have low relative velocities, and you can more effectively harden these black hole binaries. So in the extreme case of completely planar scattering, this could be a useful or effective environment to be merging black hole binaries. But in isotropic nuclei, they typically disrupted.
Are these covering the initial conditions like both within like soft and hard binaries? Yes, soft binaries.
I guess. So yeah, we don't specify. So all we do is we sample an initial orbital separation for the binary, and then we sample from a Maxwellian velocity distribution.
So when you use BAM,
Huh?
when you use BAM, the orbital velocity.
Yes, yeah. So it's 100 kilometers per
Right,
second
that's
roughly,
why.
1 AU.
Right.
Right.
That is similar to the expression velocity. So my question is, what is the set of separations you're having now?
It's about 1 to 10 AU.
So strong, so it's marginally hard.
Okay.
Yeah, yeah.
This one also didn't have any supermassive black holes.
Well, it's assumed to the expression velocity.
It does, but that's kind of why we put it at the influence radius, so that you're not really, you don't really care about it. Yeah. I think I'm almost out of time actually, but yeah, I guess maybe just one last thing. So this is just an n-body simulation with some black holes, including one particularly massive black hole with a total mass of about 200 solar masses. This is work I did with Nora Lutskendorf. And what we did is, so we have a particularly massive black hole at the very center of the cluster. And we're plotting, so this is time in gig years on the x-axis. This is mass and solar masses on the y-axis. And every time an object has a strong interaction with the central IMBH, you put a point on this plot. And so we find that the second most massive black hole quickly sinks in and finds itself in a binary orbiting the central IMBH. And then this pair systematically interacts with the remaining black hole population and ejecting them, removing them from the cluster as they interact. And so you're having these three-body interactions. And so with our analytic formalism, we could calculate what you'd expect for the velocity distribution of the ejected black holes, as well as the orbital evolution of the central IMBH black hole binary. And one other thing you notice is, so it looks like the ejection sequence tends to be in order of mass. So the most massive black holes, except for the two most massive, are ejected first, and then you end up ejecting the lowest mass black holes last. And so this kind of leads the question, so could you assign some sort of half-life to each black hole mass and use this to get an estimate for the probability of a given decay chain, or like what order will these black holes be ejected in, and can you use sort of a half-life formalism to do that? And so we've been trying to do work in this direction, looking at the basic idea. So if you take the four-body problem simulations we were just looking at, so again, 3 encounter outcomes, 2 + 1 + 1, 2 + 2, and 3 + 1 is now in green. You want to be able to fit the lifetime distributions of each, which is what we're showing here, with some sort of exponential curve, and use your fit to calculate some estimate for the half-life. So where the half-life is basically just telling you, if I have 100 chaotically interacting systems and I wait, the half-life, 50 of them will still be undergoing chaotic interactions. The other 50 will have disrupted into stable decay products. And so we've got the disruption time on the x-axis and normalized fraction of simulations on the y-axis. We go to quite a bit of trouble to try to actually fit exponentials to our lifetime distributions. I don't really have too much time to go into what exactly we did. But the basic idea is that if you can get an estimate for the half-life, then what you'd actually expect is that the ratio of the half-lives for each of these 3 encounter outcomes should be roughly equal to the outcome fractions you get for each. So if you think that the 2 + 1 + 1 scenario has the shortest half-life, then most interactions should end in this outcome. And so we extract the half-lives, we calculate that, so that is shown by the solid points. These are our calculated half-lives, and then the open points are what we get directly from the numerical scattering simulations. And so again, green, this is forming triples, 2 binaries, and 2 + 1 + 1. And what we get from our half-life formalism actually agrees quite well with what we get directly from the numerical scattering simulations and the outcome fractions for each of these decay products. And so this was all equal masses, and so we do indeed find that the outcome with the shortest half-life by far gives us the most common outcome. And so there's evidence that this is working at least with identical masses. We've also been looking at changing the mass ratios and how this affects the half-lives, finding that it works, but hopefully trying to quantify this for application to the evaporation of these black hole subclusters. And I think that's basically all I have time for. So I'll just leave up my summary slide and take questions. Thank you.
So if you go back to that boundary black hole and the center results, yeah, this one kind of. So you said there's a number of encounters before you merge. How many encounters do you expect?
About 10, of order 10, typically.
What's the actual? This is the one you need to merge.
So
What's the number of typical
encounters that we find?
typical number of encounters in that environment? Some stellar densities and so on.
So I mean, over a few tens of millions of years, you would expect of order 10 interactions to happen. So the time scale, I think, is relatively comparable to, for example, the lifetimes of the massive stars, or it's sufficiently short relative to how you get 2 black holes in a binary in a galactic nucleus is sort of a bit of a question. I think star formation is a good option. If you form stars recently, then you'll form binaries, and this is one way. But over time, in a high velocity dispersion environment, those binaries will be disrupted.
So they would disrupt before they form binary form merge.
Before they merge. Yeah, so I think
There's no much chance for them to
That's right.
a binary to another binary to form a bigger black hole.
that's right. So one of the takeaways here is that, yeah, galactic nuclei are bad places for black hole mergers. Globular clusters are much better places. You want a low velocity dispersion and a high binary fraction. And galactic nuclei will have generally low binary fractions and very high velocity dispersion. The hard-soft boundary is down at less than an AU. Unless you can put yourself in like some coplanar scenario, like that AGN disk scenario, and you've managed to grind down everything into the disk. Since there you can imagine you would have low relative velocity simply by being in a Keplerian orbit and coplanar. If anything's outside of the disk, though, then you run the risk of having a very high relative velocity and ablating your binaries.
So what needs to happen before you can put this sort of formalism into like the Monte Carlo integration?
Yeah, so I think we need to figure out what this turnover is, for sure. Actually, other than that, I think that's most of what we're missing right now.
Can you explain that again? Why you think?
Yeah, so I don't completely understand what's going on here. I mean, yeah, so this is kind of the next problem Nick and I are trying to tackle, and we've been really focusing on the 3-body case because it's a very similar problem in the 3-body case. Formally, your orbital energy distribution diverges at as your orbital energy heads towards 0, as your binary is becoming unbound. And so, but if you look at numerical scattering simulations, you see a very abrupt turnover right before you get to 0, basically. So, and then the question is why? Why are you seeing this turnover, and why does, what's happening in our simple analytic approach that is clearly breaking down? And so we need to come up with some way of imposing some sort of limitation on the integration to prevent that divergence, and figuring out where exactly this turnover point should happen and why.
So I think this was the question that Aaron was asking.
Okay,
Right?
yeah,
As you go to 0
Yeah.
energy,
yeah,
you have this problem.
You do.
That's what he was asking.
okay, yeah, and yeah, so the only thing, I mean, the thing that's kind of clicked for me is just that in having most three-body ejection scenarios, if you want to shoot something out at non-zero velocity, then you can't have an arbitrarily wide binary. If you just try to imagine that ejection scenario, you can't, because causally there's no way to satisfy the requirement of getting a non-zero final velocity and also leaving a very, very wide binary. How then to incorporate this into the integration? I'm not sure. Some recent, I've forgotten the name. There's an approach that might actually, I think this has been, the issue is actually, I think it's been studied in the quantum regime, actually. So that's where we're going. That's where I'll go next, hopefully, see if I can tie that to this.
Yeah, well, another question, maybe we can keep talking upstairs.
Sure.